Hey everybody. Today we're talking about one- and two-sided alternative hypotheses in statistical hypothesis testing. So in a statistical hypothesis test, we use sample data to determine whether a particular parameter value is plausible or not. And the null hypothesis of the test represents the assumption that that parameter value actually is the case. We write it like this: h sub 0 is that mu is equal to mu naught, where mu naught is that particular value of interest, that potential parameter value which we want to know whether it's plausible or not. The alternative hypothesis of a test contradicts the null hypothesis, and typically it's the thing that we suspect might be true and are kind of thinking we're gathering evidence in favor of. For a null hypothesis of the form mu equals mu naught, there are several different ways of formulating the alternative. In particular, we can hypothesize that the true population mean is less than the hypothesized null hypothesis value. We can suspect that it's greater, or we can just say that it is not equal. So these are all potential alternative hypotheses. The first two are called one-sided alternatives because we only allow the possibility that the parameter is on one side of the specified value, while the third is called a two-sided alternative. And each of these three contradicts the null hypothesis in a slightly different way. When setting up a hypothesis test for the mean, we have to choose between them. And you should keep in mind when you're picking a one-sided alternative in particular that when you pick the one-sided alternative, you're ignoring the possibility that the true parameter is on the other side of the null hypothesis value. For instance, if you use the one-sided alternative that the true population mean is less than the specified value, you're ignoring the possibility that that true parameter is actually larger than the assumed value. As a general rule, when in doubt, you should always choose the two-sided alternative, unless you have a specific reason to assume the population mean can't be in the other direction. The two-sided alternative is the safest and most conservative option. For instance, suppose we have an oil change business, and they claim that the average time taken for an oil change there is 15 minutes, and I worry that it's actually more and that they're just sort of misleading their customers. So this is a one-sided alternative. We're only considering the possibility that the true mean time is greater than 15 minutes. We can safely ignore the possibility that it's less. And the reason here might be, for instance, if I'm thinking about it from the customer's point of view, I'm perfectly happy if they are overestimating the time it takes to do the oil change. I'm only concerned if they're underestimating it. In this case, and in many others, the choice of a one- versus two-sided alternative really depends on the specific question that we're trying to address. For instance, in this last example, we might instead just be interested in the question of whether the business is accurately estimating the average time of their oil change, in which case the alternative hypothesis that would be appropriate would be that mu is not 15, so a two-sided alternative. In a situation like that, potentially we are working for the company and just trying to get as accurate a handle on the oil change times as possible to think about not just customer satisfaction, but also, staffing needs. Here's an example for you to try. A teaching manual claims that a certain exercise takes an average of 30 minutes. So just write down a null and alternative hypothesis for this one. So my null hypothesis is that the actual mean for the amount of time taken on these exercises is 30 minutes. In this case, I'm going to choose a two-sided alternative, that population mean is not equal to 30. We don't have any justifiable reason to rule out or ignore the possibility that the true mean is less than 30 or greater than 30. Now, one really important warning here is that both your hypotheses are set in stone at the beginning of the process, which typically means you're stating your hypotheses before the data is even collected. You should never, ever choose your hypotheses based on the sample data that you're using in your test. That is an important form of statistical malpractice. The choice of alternative hypothesis affects the way we calculate the p-value, and we'll see that through a full example of a statistical hypothesis test here with a two-sided alternative. A restaurant claims that the mean sodium content of one of its sandwiches is 920 milligrams. A simple random sample of 44 sandwiches has a mean sodium content of 925 grams. At significance level alpha equals 0.01, is there enough evidence to reject the restaurant's claim? assume the sodium content is normally distributed with a standard deviation of 15 milligrams. So again, I'm going to use a two-sided alternative here. We have no reason to rule out the possibility that the mean sodium content is below or above. So we assume the null hypothesis is true and that the true population mean is 920. We're then going to compute the probability of getting a random sample mean more extreme than the one we got just by random chance. By the central limit theorem, the sampling distribution of x bar is approximately normal. It's going to have a mean of 920. Remember, we assumed that. We assumed the null hypothesis is true. And it's going to have a standard deviation of 15 divided by the square root of 44. So 15 being the population standard deviation that we were given, and 44 being the sample size. All told, sigma sub x bar is about 2.66. In other words, that's measuring the variability on x bar from sample to sample. How much do we expect the sample mean to differ from one sample to the next? Next, we compute a test statistic for our sample. Since the sample mean x bar has a normal distribution, our test statistic is going to be a z-score. We take the sample mean we got, 925, subtract off the expected value, 920, again, expected when the null hypothesis is true, and then divide by the standard deviation of x bar, 15 divided by the square root of 44. When we do all that, we get a z-score of 2.21. And that's measuring how surprising our x bar was when the null hypothesis is true. In words, the sample mean that we got is 2.21 standard deviations above what we would have expected when the null hypothesis is true. So we now need a p-value. We want to compute the probability of randomly getting a z-score at least this extreme just by random chance. Finding this p-value amounts to finding one of these shaded areas and then doubling the result. The left of those areas is easier to compute since we're going to use the normal CDF, the cumulative distribution function, which gives an area to the left. So we'll find the probability of getting z less than negative 2.21 and double that. The command in R is pnorm of negative 2.21. As always with normal calculations, you should do this using technology. When we do pnorm of negative 2.21 and double it, we get a p-value of 0.027. Now, we set a significance level of 0.01. This p-value is greater than that. Since p is greater than alpha, we do not reject the null hypothesis. There's insufficient evidence to support the alternative that the mean sodium content of the restaurant sandwiches is not 920 milligrams. Now, I recognize that that is a bit wordy, doesn't really sound like we've concluded much, and in fact we haven't. This is not the same thing as saying that we have evidence in favor of the null hypothesis that the mean is 920. In fact, our sample wasn't 920. Our sample indicates otherwise, just not very strongly. So in the end, really, we aren't drawing any conclusions. If we want to draw a more solid conclusion, we need to go out and get a larger sample size, look at more of this restaurant's sandwiches. To summarize, to test a one-sided alternative that the true population mean is less than a specific value, we compute the probability of randomly getting a z-score less than or equal to that z. To test the other one-sided alternative that the true population mean is greater than the specified value, we compute the probability of randomly getting a z-score greater than or equal to that z. And finally, to test a two-sided alternative, we compute twice the probability of randomly getting a z-score greater than or equal to the absolute value of z. And so what that really means in practice is I'm getting the z-score, I'm making it negative, and then I'm computing the probability of getting a value less than that. Finally, I'm doubling it. In that sense, the sandwich example was completely typical. Notice that one thing all three of these have in common is that we're always computing a z-score and using that to get the p-value.